In this lecture, we're going to learn a little more about number systems. Number systems allow us to transform data from the form that is really convenient for humans in a form that is convenient for computers in these ones and zeros that you see on the left. We can also use them to do the reverse, go from ones and zeros and go in the format that is convenient to humans, like this 22 or this Steve name here. To make sense of how these number systems work, let's analyze the decimal system that we really use in daily life. And that is usually called base 10. So if you look at this 2371 number here, we can really split it in the form that you see to the right here. If you try and take this expression we have on the right here and evaluate it, you're going to get this number here. 2 times 10 to the power of 3, this evaluates to 2000, and this one here is going to evaluate to 300. This one is going to evaluate to 70, and the last one is going to evaluate to 1. And if you add these things up, you're going to end up with this number. So this is how we can take a number and make up a base 10 representation of it. We can do the same thing for 924 here or 47 here. It really is basic math. You don't need to have a lot of background in math to make sense of this. So we're going to use this exact form and understand binary numbers. If you look at what we have here, we have a few binary numbers that are made up of ones and zeros. That's why it's called binary, because you can only have 2 states, or 0 or 1 in your numbers. So we can really do the same thing. We are in base 2, so instead of using a 10 here, we're going to be using a 2, but it is the same operations we really did. If you take this and multiply and add these things up, what you're going to end up is a base 10 representation of this number. If we go in the middle here, we have something we can easily do without using a calculator. The expression on the left here is going to evaluate to 0 because we are multiplying with 0. The second one is going to be a 2 because we are taking 1 and multiplying this by 2. The others are going to be zeros, but the last one is going to be 2 to the power of 4, which is 16, and we're going to add a 2, and this is going to evaluate to 18. We can actually bring up our calculator on Windows 10. I think it can help in this a little bit. We're going to bring it up, and we want to put it in a programmer mode, and we're going to go back on our slide and find our number, which is 10010. So we're going to type it out, 10010 in binary. This is binary that we have typed here. So let's clear this and do 10010, and you're going to see that in decimal it is 18, which is what we came up by computing this in our brain. Let's try the one we had before that we couldn't really do in our brain. We're going to say 100101. Let's do that. We're going to clear 100101. This is going to evaluate to 37 in decimal. And you can use calculators like this to really do the transformations between these different number representations. Okay, down below we have a 111, which is going to evaluate to a 7 in base 10. Okay, if we have 3 digits, we can really represent numbers between 0 and 7. And you see a table here that is going to prove that. 000 is going to evaluate to 0 in decimal. 001 is going to be a 1. And if you go down to 111, that is going to evaluate to a 7. You can try and use a calculator to prove this and really understand how this works. If we use the 3 digits representation, our numbers are going to look something like this in memory. We're going to take the bits in memory and group them in groups of 3, and we are going to use binary to actually make sense of these numbers. For example, here on the left, this is going to be a 1. The second one from the left is going to be a 6, and this is going to be a 6 as well. This is going to be a 0. This is going to be a 3 because we have 1 and 2 here. We add those up, we get a 3. If this doesn't make sense, you can try and use a calculator. You're going to see that it makes sense. Okay, so what if we want to group our digits in groups of 4? We can do that, and we're going to end up with something like this. The values we can represent are going to go from 0 all the way to 15, and you can try and prove this using the calculator like we just did. And it is going to look like this in memory. So what we really are doing is grouping the bits in different sizes of data, and we have a kind of formula that we can use to make sense of the data in memory. For example, on the left here we have 0, 1, 1, 0. If we go back to our table and find 0, 1, 1, 0, this is a 6. And we're going to know that these 4 bits here are really storing a 6. And there are ways you can manipulate this in your C++ program. We're going to see that. You can also use 5 digits and you're going to end up with something like this, and the numbers are going to go from 0 all the way to 32, and this is how it's going to look in memory. You can try and come up with what this represents in decimal. I'm not going to tell you this, but we can try and figure out the one on the left here. So it is 0, 1, 1, 0, 1. If we go back, we're going to come up to 0, 1, 1, 0, 1, which is a 13 here. So this memory location, these 5 bits represent a 17 number. So if we want to kind of generalize what we have talked about in the last slides, if you have 1 digit, you can really represent 2 states, 0 and 1. If you have 3 digits, you can represent numbers between 0 and 7. And you can go all the way down. And if we generalize this in a mathematical formula, we can say that if we have n digits, we're going to be able to represent between 0 and 2 to the power of n minus 1. And if you try to plug in any number of digits, you're going to see that this formula works. Okay, so these are a few grouping of bits we have in practice. We can use 8 digits and we can represent numbers between 0 and 255. If we have 16 bits, we can represent this range. If we have 32 bits, we can represent this range. If we have 64 bits, we can really represent a really huge range. I can't even say this number. It's really big. Okay, now you should have a pretty good idea of the binary system and different representations we can use to make sense of binary numbers in a computer's memory. The last thing I want you to see is what we call hexadecimal number system. And it is a technique we use to shorten the length of how we represent a binary number in memory. How does it work? Well, we take our number and split it in groups of 4 bits. And each group is assigned a symbol we can use to represent it. If we have 4 zeros, that's going to mean a 0 in hexadecimal. If we have 0001, we're going to represent a 1. And you can see that if we go up to 9, this is really similar to what we have in the decimal number system. But once we hit 10, we're going to represent that with an A in hexadecimal. 11 is going to be B, 12 is going to be C, 13 is going to be D, 14 is going to be E, and 15 is going to be F. So how do we use this to represent binary numbers? Let's see an example. Here we have a huge number that we represent in memory. It starts with 0 and ends with a 1 here. So the first thing we're going to do is to split this in groups of 4, and the one on the left is going to be a 1, 1, 1, 1. If we come back to our table here, 1, 1, 1, 1 means F. So we're going to represent this with an F. If you go to the second group of 4 bits, we have 0, 0, 1, 1. If we go back, 0, 0, 1, 1 means 3. So we're going to have a 3 here. I hope this makes sense. And we're going to keep using the same transformations, and we're going to come up with 1F03E6. And we can represent this binary number using these symbols. You can see that we go from using 32 bits to using 1, 2, 3, 4, 5, 6, 7, 8 symbols to represent this. And this is shorter and easily manipulable by humans. And we use a 0x in front to mean that this is a hexadecimal number. I really hope this makes sense. So if we have numbers that don't really fit in groups of 4, we're going to go from the left and split this in groups of 4. And we're going to end up with a group on the left that doesn't really meet our requirements. And what we can do is add the missing bits and make them zeros. And we call this operation padding. This is what you can do to really represent any number in hexadecimal if you don't have enough bits on the left. We also have another system that is really not widely used today, but I am mentioning it here for completeness. It is called octal system. It goes from 0 all the way to 7, and we can divide our binary number into groups of 3 and represent using these zeros and ones to shorten the length of the binary number. We can really do the same thing we did with hexadecimal. So we're going to take our binary number and divide this in groups of 3. The one on the left is going to evaluate to a 7 because it's 1, 1, 1, and 1, 1, 1 evaluates to 7 in octal system. The second one is also going to be a 1, 1, 1. The third one is going to be 1, 0, 0. If we go in our table, it's going to be 1, 0, 0. It's going to be a 4, and you see we have a 4 here, and you can do the same things until you have figured out the entire number here. And you see on the left we are doing padding and adding a missing bit and making it a 0. So we are coming up with 0, 0, 1. And if we go back to our table here, 0, 0, 1 is a 1. And that's what we put here. So we're going to put this number here. It's going to be 15, 61, 41, 70, 47, 7. And we're going to add a 0 in front to mean that this is a number represented in the octal system. I really hope this makes sense. Okay, so we have seen all these binary numbers and different number systems we can use to represent them, but how do we use them in a C++ program? Well, I'm glad you asked. Here is a simple example of how you can represent the number 15 through different number systems in C++. If you just say 15 like this, it's going to be in decimal. If you add a 0 in front, it's going to mean that the number is in octal system. So this can be confusing sometimes. If you do 017, it's not going to be 17. So if you say 017, C++ is going to interpret this number as if it is in octal system, and it is going to turn this into 15. Down here you see the same representation in hexadecimal. We saw that you use a 0x in front to represent that it is in hexadecimal, and this is going to be 15 in memory. And here we have representation in binary using zeros and ones, and you use 0b in front like this. I have to say that this was only possible since C++ 14. So if you are using an older standard of C++, you won't be able to represent binary like this. And if we run this program, it is going to print the same thing. It is going to print 15, but we stored the number using different number systems. Let's go to Visual Studio Code and try this out. Okay, here we are in a folder I have on my system where I am going to be storing my projects for this chapter. The first thing I am going to do is copy code from our template project. I am going to go in and copy things over, and I am going to put these in 4.2 number systems. I am going to open this folder in Visual Studio Code, so I am going to go to File, close the folder we have now, and I am going to open up a new one, Open Folder, and I am going to browse to the location of my project. I am going to open this project here that says Number Systems. We are going to get rid of the welcome screen and open our main CPP file. We're going to get rid of this const eval thing and clear everything we have in the main function here. The first thing we want to do is to store an integer that is 15, and we're going to say int number1, the exact same thing we had in the slides, and we're going to store 15 in this variable here. This is going to be represented in decimal, and if we want to store the same number in octal, we saw that in our slides we could store this as 017. So let's do that. We're going to say int number2, and we're going to store in 017. This is not going to be 17. This is going to be a representation of a number in octal system. So we're going to say that this is octal, and we can represent the number in hexadecimal as well. So we're going to say int number3, and it is going to be 0x because it is hexadecimal, and we're going to say 0f. This is how we represent it. You can use lowercase or uppercase, it won't really matter. Let's use uppercase here. And we can use binary because we are using C++ 20. So we're going to say int number4, and we're going to store in a representation of 15 in binary. And it happens to be 4 zeros and 4 ones. And we have to prefix this with a 0b. This is how it works. So this is going to be in binary. And if we print all these numbers up, we're going to see, let me not tell you this. What do you think we'll see? Okay, so I went ahead and typed this out. What do you think we will see when we build and run this program. Before we do that, we're going to open a terminal so that we see it here. And we're going to go to terminal, run task. We're going to build with GCC. Let's wait and see if the build is successful. Build finished successfully. We have our Rooster program in here. We're going to click somewhere in this terminal and our terminal is going to show up. If we do dir, you're going to see that our Rooster program is here. And if we run it, I want you to take a moment and guess what we're going to see. Number 1, 15, number 2, 15, number 3, 15, and number 4, 15. This is really the same number we are storing in these variables, but we are using a different representation that is going to be convenient depending on whatever it is we are doing. If it is more convenient to use binary, we're going to use binary. If it is more convenient to use hexadecimal, please do use hexadecimal. But the representation of this number in memory is really going to be the same. I really want you to take some time and let this sink in, because you're going to see these things a lot of times in your career as a software developer. So please do yourself a favor and make sure you really understand this. Okay, this is really all we set out to do in this lecture, trying to make sense of the binary numbers we have in memory and how we transform between them and different forms of data that is easily manipulable by humans. All data is represented by a bunch of grouped cells of zeros and ones. We have seen this. As the range of your data grows, so will be the number of digits you need to represent the data in memory. We have seen that the hexadecimal system makes it a little easier for humans to handle streams of data in ones and zeros. Octo has the same goal as hexadecimal, but it's almost no longer used in modern times. I just mentioned it here for completeness. We are going to stop here in this lecture. In the next one, we're going to look at integers in a little more detail. So go ahead and finish up here and meet me there.